Next is the periodic trends in the properties of elements. This means in this section we will discuss the periodic trends in the certain physical and the chemical properties and try to explain them in terms of the number of electrons and the energy level. See first the physical properties. There are numerous physical properties of the elements such as melting point, boiling point, density, heat of fusions and vaporization like this. That is the energy of atomization, etc., which shows the periodic variation. However, we shall discuss the periodic trends with respect to the atomic, ionic, ionization, ionic radii, ionization enthalpy, electron gain enthalpy, and the electronegativity. First, we will discuss the atomic radius. The atomic radius, you can very well imagine that finding the size of an atom is a lot more complicated to measuring the radius of a ball. That means because the size of an atom is very small. That means there are 1.2 into 10 power minus 10 meter. So meter in radius. It's very small. So since the electron cloud surrounding the atom does not have any sharp boundary to determination of the atomic size cannot be precise. In other words, that is there is no practical way by which the size of an atom, individual atom, can be measured. For example, they estimate the atomic size can be made by knowing the distance between the atoms in the combined state. For example, chlorine Cl2, this combined state, it means Cl having Cl like this. The combined statement, that is Cl2, they have a covalent bond. Cl2 have a covalent bond because Cl bond. Here the Cl2 having, this is also called the covalent radius. This is a non-metallic element. Here the the bond length, the chlorine molecule bond distance is 198 picometer, and half of the distance is 99 picometer is taken as the atomic radius for the chlorine. Here the chlorine atomic radius is what? 99 picometer. Then for in metal, this is for non-metal. In metals we define the term is metallic radius, which is taken half the internuclear distance separating the metal cores in the metallic crystal. Example, the distance between the two adjacent atoms of copper. The copper atoms in solid copper, that is 256 picometer. Here the metallic radius of the copper assigned the value as the half is what? 128 picometer. So simply in this book we are used the term is called atomic radius. The atomic radius is referred to both covalent or metallic radius depending on whether the element is a non-metal or a metal. So atomic radius can be measured X-ray or the other spectroscopic studies. Now look at some atomic radius are given, that is atomic radius across the period and down the family. The atomic radii, that is, we can explain these trends in terms of the nuclear charge. That's nuclear charge in the energy level. So the atomic size generally decreases across the period. Look at here, 152 picometer for lithium, beryllium 111 picometer, boron 88, carbon 77 picometer, nitrogen 74. That means across the period, here the atomic radius decreases. Across the period, atomic radius decreases. So the elements in, this is the second period. Then elements in the third period, that are sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. Here also 186, 160, 143, 117. So atomic radius decreases across the period. That means here because within the period of the outer electrons are the same valence shell and the effective nuclear charges increases as the atomic number increases, resulting as increased in the attraction of electron of the nucleus. So within a family, look, this is the family or vertical column of the periodic table. The atomic radius increases regularly. Look at here, lithium, sodium, potassium, group 1 elements and the group 17 elements. Look at here, 152 picometer, 186, 231, 244, 262 picometers. That means increases with increases atomic number. So that for alkali metals in the halogens, that is, as we descend the groups, that is the principal quantum number increases and the valence electrons further from the nucleus. This happens because the energy levels are filled with the electron, which serves to seal the outer electrons from the pull of the nucleus. So consequently, the size of an atom increases, reflected in the atomic radii. Here, the noble gases, that's the atomic radii of the noble gases are not considered here, because the being a monoatomic of their values are very large, that is the non-bonded radii. In fact, the radii of noble gases should be compared not with the covalent radii but with the van der Waals radii of the other elements. Next is ionic radius. Next, ionic radius. The terms says ions means what? There is involvement of cation and the anion. That is the removal of electron from an atom, that is called cation. Gain from the that is gain of the electron, that is called anion. So the ionic radii can be estimated by measuring of the distance as cation and anion in a ionic crystal. So in general, the ionic radii of element exhibit the same trend as the atomic radii. A cation is smaller than the parent atom because it has the fewer elements, while its nuclear charge remains the same. So cation, for example, magnesium, they have a positive charge, so that Mg2 plus is the cation. Then, for example, chlorine is anion, chloride ion, sulfate ion, SO4 2-, like this. So they are anions. The cation is smaller than its parent atom because it has a fewer elements, while its nuclear charges remain same. So the size of anion will be larger. So this is smaller and this is larger. That is, the addition of the one or more electron would result in the increased repulsion among the electrons and the decrease in the effective nuclear charge. For example, in the fluoride ions, that is the fluoride ion, the 136 picometer, the ionic radius, then the atomic radius of fluorine is, that is fluorine F2, is only 64 picometer. This is 136 picometer, this is 64 picometer only. That is the atomic radius of sodium is 186 picometer compared to the sodium ion, that is Na plus. The value is 95 picometer. So we find some of the atoms and ions which contain the same number of electrons is called isoelectronic species. Isoelectronic species. That means as atoms and ions which contain same number of electrons. Example, O2 minus, F minus, Na plus, Mg2 plus. So these are isoelectronic species. Example. Why? Look, what is the atomic number of oxygen? 8. What is the ion here? The anion. So anions mean addition of the electrons. So gaining. Here 8 plus 2, 10. Here fluorine atomic number is 9. What is the charge? Minus 1. So that 9 plus 1, 10. Then sodium, the atomic number is 11. Here the cation, that is the positive charge. Positive charge means lose the electron, so remove the electron. What happens? 11 minus 1, it will become 10. Mg 12, the cation is 2, so that minus 2, it will become 10. So the same number of electrons are present, so that these are called isoelectronic species. Their radii would be different because of their different nuclear charges. The cation with the greater positive charge will have the smaller radius because of the greater attraction of the electron to the nucleus. So anion with the greater negative charge will have the larger radius. In this case, net repulsion of the electrons will outweigh the nuclear charge of atom, and ion will be expand in sizes. Look at this. In the following species, which will have the largest and the smallest size. Which one is the largest size and the smallest size? Here, the largest species is magnesium and the smallest species is aluminum 3 plus, Al 3 plus. Why? The reason is what? Here, the magnesium, the atomic number is 12. Here, the aluminum, the atomic number is 13. But in magnesium, there is no in free state, but here the combined form, so that it have plus 2 oxidation state. That means removal of 2 electron, it will become 10. This is 2, 12. And aluminum 13 atomic number, removal of 3 electrons mean that is 10. So here the largest species is what? This, and the smallest species one is the aluminum, because of the number of electron you have to consider. The atomic radius decrease across the period. The cations are the smaller than the parent atom. So among the isoelectronic species, the one of the larger positive nuclear charge will have the smaller radius. Suppose if you add Al also, same thing. So here the largest species magnesium and the smallest one is aluminum. Next is the ionization enthalpy. The quantitative measure of the tendency of element to lose electron is given by its ionization enthalpy. It's represented the energy is required to remove an electron from an isolated gaseous atom. That is isolated gaseous atom, X gas. That is here first ionization enthalpy for element X gas is enthalpy change. That is the enthalpy change means delta IH. So this indicates enthalpy change for the reaction X gas. 1 electrons lost from this. So the ionization enthalpy, usually the unit is expressed kilojoule per mole. We can define the second ionization enthalpy of the energy required to remove the second most used, that is X plus gas. So this is the first ionization enthalpy. This is second ionization enthalpy. X2 plus gas and electron. So the ionization enthalpy is the energy required to remove the second most loosely bound electron. So it is the energy required to carry out the reaction. So the energy is always required to remove electrons from an atom, and hence the ionization enthalpy is always positive value. So the second ionization enthalpy will higher than the first ionization enthalpy. So this is higher compared to this. So here the first ionization, because it's more difficult to remove electron from the positively charged ion than from the neutral atom. So this is the neutral atom. So in the same way, the third ionization enthalpy will be bigger, that is higher than the second one. The third ionization enthalpy, suppose third ionization enthalpy, this will be a higher one. The term ionization enthalpy is not qualified as taken as a first ionization enthalpy. Then the ionization enthalpy of an atomic radius are closely related to the properties. To understand these trends, we have to consider two factors. That is, one is attraction of electron to the nucleus. Attraction of electrons towards nucleus, and the repulsions of the electron from each other. So the effective nuclear charge experienced by a valence electron in an atom will be less than the actual charge of the nucleus because of the shielding or screening. It means in the valence screening or shielding means the valence electron from the nucleus by the intervening of the core electrons. For example, 2s 2s electron in the lithium is shielded from the nucleus by the inner core of the 1s electron. For example, the 1s the first lithium, the atomic number is what? 3. So 1s 2, 2s 1. So here the 1s electrons are shielded by the 2s electron. That means the first cell, K cell, is shielded by the L cell. This is the nucleus. That means this is by shielded. So here, as a result, the valence electron experiences a net positive charge, which is less than the actual charge of the +3. Then in general, the shielding is effective when the orbitals in the inner shell are completely filled. The situation occurs in the case of the alkali metals, which have the single outermost ns electron preceded by the noble gas electronic configuration. So suppose when we move from the lithium to fluorine across the second period, the successive electrons are added to orbitals the same principal quantum level, and the shielding of the nuclear charge by the inner core of the electron does not increase very much to compensate for the increased attraction of the electron to the nucleus. So in across period, the increasing the nuclear charge outweighed the shielding. Consequently, the outermost electrons are held more and more tightly. So the ionization enthalpy increases across the period. So across the period, the ionization enthalpy is increases. As we go down the group, the outermost electron, the outermost electrons increasingly, there is increasingly further from the nucleus, there is the increased shielding of the nuclear charge. So the electrons in the inner level. So in this case, increasing the shielding outweighs the increasing the nuclear charge, and the removal of the outermost electron requires the less energy down the group.